Right, here we have a problem that's dealing with calculation of a percent yield. Remember, we talked about the idea in class, we talked about the idea of chemical reactions not always being 100% efficient. We don't always get out of it everything that we think we should be able to based on what our stoichiometric calculations are. And so we have to have some way to measure, how much of what we should actually be getting out of this chemical reaction are we really ending up with. And there are going to be two terms that we're going to talk about here in a second, an actual yield and a theoretical yield, as well as a percent yield, and we will talk about and define those in a second. But what we would like to do first is, it says we have 500 grams of carbon monoxide, and notice that that's written in a little bit different way than you're used to seeing 500 written. Written in scientific notation as 5.00 times 10 squared. The reason for that is that we want to express 500 to three significant figures. That's why we've written it this way. It's reacting with excess hydrogen gas, and it tells us how much methanol is produced. Now, remember that we looked at, or we talked about this idea of percent yield, where percent yield gives us a measure of a roughly, gives us not a rough measure, but it gives us a measure of how effective or how efficient our reaction is performing. And it's based on the ratio of actual yield and theoretical yield, where actual yield is the actual amount of stuff that you produce in the laboratory, and theoretical yield is what you calculate you should be able to make in the laboratory. In theory, we would hope the actual yield and the theoretical yield would be exactly the same, but it is not like that for most chemical reactions. We take that ratio and multiply by 100% to turn the ratio into the percent, or the fraction into the percent, and we end up with what we would call our percent yield. 100% yield would be good. It would indicate that the actual and theoretical yield are the same. 0% yield would be bad. It would indicate that we don't get any of the product that we want, and even though we predict that we should be able to make some. So what we're given in this problem with the 485 grams is we're told the actual yield of that chemical reaction. We're told, okay, if we end up with 485 grams of methanol, CH3OH, all right, what's the percent yield? So we need to first know, because we want to know the percent yield, so we want to calculate this. We have the actual yield. What we need to find next is we need to find that theoretical yield. What's the calculated amount of methanol we should be able to produce? And we've got our .500 grams of carbon monoxide, and we're reacting that with excess hydrogen gas. When we hear excess, that just means that we have so much of it that it's going to be there, and it's going to be left over when we get done. It will be the excess reagent. It's telling us that carbon monoxide is the limiting reagent. So, in a way, a regular stoichiometry problem that's not limiting reagent, when they tell us what is in excess, or that there is excess of one of the reagents, they're telling us that the other must be, if there are two of them, the other reagent must be the limiting reagent. We want to calculate how much carbon monoxide, or how much methanol we can produce from the carbon monoxide. So this is a stoichiometry problem. We've got to get to moles of carbon monoxide. We're going to use the molar mass for that. I'm not going to walk through how to calculate it, but it's 28.01 grams of carbon monoxide in 1 mole of carbon monoxide. Now we've got to moles. We can use the balanced chemical equation, 1 mole of carbon monoxide to 1 mole of methanol. Moles cross out. Now I know the molar mass of methanol. 1 mole of methanol is 32 0.05 grams of methanol. Moles crossed out, and I'm left with grams. I now have calculated how much methanol I should be able to produce from 500 grams of carbon monoxide. And you punch that into your calculator, and you should end up with 572 grams of methanol, which is going to be our theoretical yield. That's our theoretical yield. How much should we be able to produce? At this point, it becomes a plug and chug problem because this is no longer a circle check mark. We know that theoretical yield. You know those two numbers, 100% is given, we can calculate our percent yield. So our percent yield is our 485 grams that we actually produced, our 572 grams that we should be able to produce theoretically, multiply that, divide, and you end up with 84.8%. About 85% is what we should end up with for this calculation. Now, a lot of times students will say, is that actually a good percent yield or not? And in reality, it's probably going to depend on the chemical reaction that you're running. But generally, people would say that 85% yield is pretty good. Again, it's going to depend on what you're doing. But for the most part, if you're doing a reaction where you need to report the percent yield and get 85% or 80% or higher, generally you've done a pretty good job. Some chemical reactions that are very difficult to run, we might even say that 50 or 40 or 30% would be a good yield for that chemical reaction, just because they're a little bit stubborn and they don't like, sometimes compounds don't like to react in the way that we want them to. So that generally would be considered a pretty good percent yield. I'd guess that you'd get pretty good marks for that if this were a reaction you were running in lab. So that's how you work through a problem dealing with percent yield, actual and theoretical, how you would find those, plug them in, and use that percent yield calculation.